All right, welcome. So in this video, I want to talk a little bit about some of the key concepts of complex systems that are going to be useful for us as we explore simulating complex systems. The first concept that I want to introduce is the concept of complexity. Now, complexity is a little bit hard to define, and within the field of system science and complexity science, there are a number of competing definitions of complexity that can be useful for different purposes, and depending on what your purpose is, you might like one over the other. Part of the goal of system science and complexity science is to search for a unified theory of complexity that would apply to all of the fields that have complexity involved. But at this point, we don't really have a unified theory, and so we don't really have one to present. So instead of saying really what complexity is, I'm going to say maybe what it isn't. What is a simple system? And so I've got a statement here saying that complex systems don't yield to analytic predictability like simple isolated systems. So simple isolated systems are going to be the contrast to which we define complex systems. And simple isolated systems are what we're used to. Now here I've got an equation. This is an equation that you can form from Newtonian mechanics. This is the equation for the change in the position vector of a particular object over time given a particular velocity vector. That is, the change of position over time is equal to the old position plus the velocity vector times the amount of time that has occurred. Now, we've been using this in our simulations to allow a discrete advance of a simulation by, say, one tick. The t here represents the one tick, and then we might have built into our entities some velocities and positions. In Newtonian mechanics, we can use these types of equations to solve for the position of an entity given any amount of time. So, for instance, in a simple isolated system like a moon orbiting a planet, if we know the moon's initial position relative to the planet, and we know its initial velocity relative to the planet, and we know how much time has passed since that initial position, we can calculate exactly where the moon is after that period of time. And this is what we sometimes call analytic predictability. The analytic bit is that we just need to do a little analysis by doing some math, plugging some numbers into an equation, and then the prediction is predicting, hopefully, the future state of the system. This type of predictability tends to work only on simple isolated systems, and that's why if you've studied some Newtonian mechanics in the past, usually the very first thing your professor will say to you is something along the lines of, well, imagine we have a moon and a planet, but they're alone in a vacuum and there's nothing else there. The alone in the vacuum is the simple isolated system, and luckily for most of the science that we've done in the history of humanity up until now, our science has yielded to simple isolated systems, meaning that by taking a more complex system that we see in the universe and then assuming it is a simple isolated system that has no environment, that has led to some productive theories like Newtonian mechanics. Even though we know when we try and apply those theories to the complex systems in the real world that they are not simple isolated systems, but like I said, a lot of the times we've still had a lot of great success with that. Let's take a look at a simple simulation that I've created here of a moon orbiting a planet. And for the parameters that I created here, I just did a quick Google and I decided to make the moon and the planet's ratio in mass to be effectively the same as Earth's mass and Earth's moon. That's about as much of the realism that I've programmed into this simulation. Otherwise, I've just got an arbitrary force of gravity that is applied between both of the two objects in the simulation, or all of the objects if I were to add more moons into the simulation. And at the moment, the moon, as we can see, is orbiting fairly smoothly around the planet. And the orbit itself is one that the moon will repeat over and over again and again using those analytic predictability. Here I've got a simple isolated system, and using those formulas of analytic predictability, we should be able to predict exactly where the moon will be in its orbit in any amount of time that we want. It is maybe worth noting that it's not exactly trivial to compute it because this orbit, the axis of orbit, as you might be able to tell, is ever so slightly rotating in the counterclockwise direction. The moon itself is orbiting clockwise, but the axis of its rotation is rotating counterclockwise. But nonetheless, that's something that we could include in our equations to predict where the planet would be, or rather where the moon would be relative to the planet after some fixed amount of time. We could take into account that the axis is rotating as well and use that to compute where the planet would actually be. So this is a simple isolated system in which we can rely on some analytic predictability to predict where the moon is. But in contrast then, a complex system is one in which we cannot apply our analytic predictability, just plugging in some numbers into a formula to predict where our future entities will be. And instead, we are, at least at the moment, reliant only on simulation to determine where those entities will be. Meaning, if we want to know where the moon is going to be in 1,000,000 years, the only technique that we have available is to just wait 1,000,000 years and see where that moon is. Now, one reason for that is because complex systems display what we call non-linearity. And so what I have here is a statement, a little bit of what that means to us. A complex system is going to have differences depending on the differences in its context or its environmental conditions. So what we're saying here is we're bringing in that idea that, yes, we've thought of this system as being a simple, isolated system, but now we're bringing into the fact that in the real universe, no system is a simple, isolated system. Every system has a context or an environmental conditions in which it is embodied, and that context and those environmental conditions are important to the behavior of the complex system. So this moon's been orbiting for a while, and it started at one fixed speed. I'm just going to go down here and change the fixed speed. I'm going to increase it by 1 tick, and I'm going to click my restart button, and we can see that the moon is again orbiting. And in fact, the differences between this orbit and the orbit we just witnessed are so small we probably can't tell them. This orbit is just this different shaped ellipse. It's probably a little bit larger ellipse. Now the differences between this orbit and the orbit that we were just looking at can be characterized in two ways. First, the initial difference was the difference in the initial speed between the two moons when we started the simulation. That was the difference in the initial conditions. That translates into differences in position of the moon over time. But we will call this a linear difference because the amount of difference in position between this moon and the moon on the other orbit after a fixed amount of time is a linear function of that amount of time, meaning the longer we travel in time, the bigger the difference there could be between the two moons' positions. But the smaller the amount of time, the smaller the difference. And we call this a linear difference, and most normal, simple systems have these type of linear differences. We speed up the initial conditions a little bit, and after a fixed amount of time, we can predict how much faster that particular simulation will be going. And now I want to focus on the idea of a non-linear difference, and that is that the amount of difference that is between, say, the planet in one orbit and the planet in a second orbit, given a certain amount of time, is no longer a linear function of that amount of time, meaning the amount of change that could happen could be much greater than the linear change that we would expect of simple, isolated systems. Now what I want to do is I want to show you a non-linear difference. And now the way I'm going to do that is I'm going to be adding another moon, but instead of adding it sort of perfectly on the opposite side of the Earth, I'm going to add it at a 90-degree angle, and let's see what happens. So the first thing we'll notice is that we sort of have a moon behind and a moon in front. The moon that's behind actually accelerated its orbit due to being pulled by the moon in front of it, and the moon in front of it slowed down. But what happened there was we had some sort of weird, chaotic interaction between the two of them, and now the location of one moon is flying away. It's zooming its way out of the orbit, and in fact it has escaped the orbit of the Earth. It's now gone. Due to the deterministic nature of the simulation, it will always go through the same steps if I start it over again exactly the same way. However, that it went through this sequence of steps is completely unpredictable from its initial conditions. When we started off in this condition, we have no inclination that there's going to be a sort of catastrophic interaction between our two moons at some point. This first interaction that we just saw there caused the disturbance in their orbits that led to this second interaction, and predicting both of those is something we can't do with just simple Newtonian mechanics. The only way we can do that is by running this simulation and watching it happen. Now, this is due to the non-linearity of the complex system, and it's also something that arises due to the fact that we've added a second moon here, and we now have three bodies. This is sometimes famously called the three-body problem in physics. But at least now that we've watched it a few times, we know that, hey, around that, I don't know when it was, about the 900 tick mark, we had this weird collision and we ended up in this final state. Now this state is a little bit more stable, but up until that point, we were experiencing something that we sometimes call chaos. Now here's a scene from the famous Jurassic Park movie where Jeff Goldblum tries to explain to Laura Dern what chaos theory is by dropping a drop of water on the back of her hand. And the implication that he's trying to make here is the behavior of that drop of water is going to be sensitive, and he says, to maybe small imperfections in her hand, or as I want to express it, into small differences in the initial condition. So that the chaos might arrive in a complex system if we change the initial conditions ever so slightly. It might arise in a massive change in the behavior of the system. So I'm going to do that. I'm going to make a slight change in the behavior of our system. I'm going to slow down the system by 1 tick. Again, the initial pattern is similar. One of our moons speeds up, the other one slows down. But the question is, are they going to have that catastrophic, oh, they had a bigger catastrophe even earlier this time. They actually collided, and then one of our moons smashed into the Earth. That was terrible. And well, let's zoom out a little bit and see. The one that collided with the Earth had sort of a collision artifact there and was just flung all the way out into space. But the other moon, it looks like, has established a very wide orbit now. Very, very wide orbit. So just by changing the initial speed by ever so slightly, decreasing it by 1 tick, and then according to my slider here, that was 10 pixels per second. By slowing down my moons by 10 pixels per second, we settled into this wide orbit instead of the other conditions which settled into one very narrow orbit. Now what I'm going to do is speed it up from our initial settings by exactly 1 tick, and let's start again. So now we're going 10 pixels per second faster than our original simulation. Now in our original simulation, by about 1,000 we had already crashed into each other. It looks like we had that first initial, this is where we were going to have the crash or the catastrophic. Well, it looks like by speeding us up ever so slightly, these moons have at least avoided that initial catastrophe. And here I am trying to see, every time they spin close to each other, I am sort of on the edge of my seat. Are they going to crash? And this is the idea of chaos in complex systems, is that we can't predict if, or if they are, when, that these two will have a catastrophic interaction, and one of them might fly off into space or another one might crash into the Earth. This is unknown to us. This is the uncertainty that we have related to complex systems. Now, further, in watching this, one possibility is that we actually settle into a steady state, some kind of a stable orbit, very similar to what we saw, and what we also saw with our two bodies orbiting. When they were on the opposite side, they were actually in a stable orbit, one where we would never have a catastrophic collision. And this is back to some of that chaos that I'm talking about here, is that unpredictability, meaning the only way that we know of, at least at the moment, there's no sort of analytical predictable way for us to predict if they're going to collide. We have to just simulate and watch them and see if they collide. Now the problem with that is if they don't collide, we have to watch them forever to see if they will actually stay in a stable orbit forever, or at least they will have to approach what we call an attractor state, which is a stable state like some of the orbits we've seen before, that we can predictably know that they're going to repeat that same state over and over again, at least so long as the their environmental conditions remain the same. So I think I'm going to let this run for a little bit because I anticipate that there is going to be some kind of collision or chaos at some point, but for now it seems like these two moons are following a fairly linear and predictable orbit. So I've let it run now for 20,000 ticks, and it looks like we still have two fairly stable orbits, a sort of smaller one and a larger one. It's potential that these stable orbits could continue for a very long time. One thing we'll notice is that they're no longer sort of at that 90-degree angle to one another. The planet that's sort of in the leading position has sort of led a little bit further and is maybe taking that angle, has bent it a little bit more than 90 degrees, and it's potential that if we continue this, that angle would continue to increase up to some limit. I'm not certain what, because it depends on the system. Now it looks like they're getting a little close there, and we had just a little interaction there. Yes, they've knocked themselves into new orbits. And again, this is that chaos coming into play. Maybe I'll zoom out a little bit to see if we've lost that planet. No, that planet has just entered a very wide orbit, and we now have sort of a small orbiting planet and a wide orbiting planet. Now this is very similar to what we actually have in our solar system. We have planets of different orbits. And it's possible that the way they settled themselves into these orbits is by some kind of interaction similar to this. Now, one thing we'll notice here is maybe unlike the planets in our solar system, the orbits of these two planets actually still coincide or overlap there on the right-hand side, and that gives us the potential for more interaction. As this planet comes in, depending on where that smaller planet is in its orbit, we're going to have these two interacting with one another. Now keep in mind, that's going to give two possible effects on our moons, either speeding them up in their orbit or slowing them down in their orbit based on the gravitational pull of the other moon, depending on where it is. Is it in front of it? Then it will speed it up. If it's behind it, then it will slow it down. And I think we've been getting speed up with our orbits thus far, because you can see here that our moon is flying out. It's got further than it was before. It keeps getting wider and wider, meaning as it comes down and approaches this other moon here, it's speeding up and it's accelerating in its orbit. Now, that means that this moon is probably slowing down because it's being pulled backwards by the other one. But every interaction is different. So again, we see how this circle has got narrower now. That's because this moon slowed down and the other moon is probably speeding up again. So this very wide orbit of this second moon, this could remain stable for a long time, but I've run the simulation before, and as we're going to see here in a second, we're going to get a very interesting interaction between these two moons as they approach now. And that's because they're so close together that the gravitation of the two of them caused them to almost collide. And they wibble around each other a few times before establishing themselves in some new orbits. I think maybe they'll wibble again. They got really close again. And this is the kind of chaos we can't predict on any one orbit here if they're going to. Now looks like we need to zoom out a little bit because we have established a fairly large orbit. Well, they've got, it looks like again, into another sort of stable pattern where we have one small orbit and one large one. But as we just saw, that this interaction can continue to cause chaos if they get too close to one another, and we might see that again. And in fact, I've run this simulation before. If we run this out to about 50,000 ticks, we will see that there will be a final catastrophe where one of these moons gets launched off and escapes the gravitational pull of the Earth, and the other one remains in orbit. Maybe just play with the chaos a little bit more. We could add another moon in. This is sort of an interesting simulation. I haven't run this one very much, but we can see the moon on the right has sort of sped up, the moon on the left has slowed down, and the moon in the middle is sort of going in a little bit more chaotic pattern, speeding up and slowing down depending on when it interacts with those other two moons. And again, because we have three moons now, the potential for chaos is very high. If any two of these interact in any of their orbits, we could get some very bizarre interactions. While I encourage you to play with this yourself if you want to try out some different ones, what I want to do now is talk about another property, sort of two final properties that are closely related to one another. And the first one here we call emergence, and the second one self-organization. So first I start with a quote from Aristotle. Aristotle here is on the right, and this is him talking to his teacher and mentor Plato. And this famous quote from Aristotle where we say the whole is greater than the sum of its parts. This is the idea of emergence, the idea that just the moon and the earth itself may be able to form something new. An orbit pattern, a stable orbit, is something new that emerges from the interaction between its parts. So this is the idea that the whole is greater than the sum of its parts. And this is tied closely to another principle or another concept, the concept of self-organization, or spontaneous order, as it's also sometimes called, which is that in these chaotic worlds, in this chaotic environment and universe, that amongst the chaos, order can arise spontaneously and self-organize and form into simple systems. Those systems can then themselves organize into higher order systems. And this is the way that we have sort of our subatomic particles organizing together to form, atomic particles, and then atoms settling into stable states to form molecules into biochemical states, into biological organisms, and so on. All of this emergence that has occurred level by level in maybe the evolution of human beings, but this is also an emergence that happens that we can see that creates new forms of life form at higher levels, all the way up to things like our intelligences, our individual intelligence, our collective intelligence, concepts of justice and love, and so on. These all emerge out of the interaction of simple particles. And so this power is a power that I find very, very interesting and compelling. And so it's one of the reasons why I like to study complex systems, is I want to study how emergence works. And I'm particularly interested in how the human system emerged, how human intelligence emerged, and human social systems emerged. And so I use complex systems to study that. So now, to study emergence, I do want to look at two good examples of spontaneous order or self-organization. And the first one I want to look at here is using we already looked at this one earlier, two moons on opposite sides. When we have two moons on opposite sides, as I mentioned, the gravitational force on the Earth is exactly equal, so it didn't end up moving. And the gravitational force on each other, it does impact one another, but because they're in these sort of perfect synchronous orbits, just like we saw with the single moon, the axis of their orbits does rotate as well. They're rotating in a clockwise orbit, and the axis of rotation is rotating in a counterclockwise orbit, same as we saw before. But otherwise, they are almost identical as before. They're in a stable behavior pattern. And I have actually run this simulation for a very long time, overnight, to over 1 million ticks. And after 1 million ticks, these two planets are still in a very stable orbit. Now, I say that only because I don't know if after 1,000,001 ticks they crash or they have some kind of chaotic interaction. But at least for now, and at least without any outside interaction by another moon or asteroid flying by, these two moons and the Earth here are in a stable orbit. And this is maybe more consistent with the types of stable orbits we might find out in the solar system or in other solar systems for moons around planets or planets around the sun. Now, this is a good example of a spontaneous organization. Now, just because I did this doesn't mean we're necessarily always going to get a nice stable state like this. I tried to do this also with 4 moons. Let's try it with 4, where they're all on equally distant sides. So each one is under the exact equal forces of every other moon because of the symmetry of the setup. And my hypothesis is that they should follow this same pattern forever, the same way that our 2 moons did. However, by increasing this from just 2 bodies we're trying to keep in some kind of simultaneous orbits to 4, we've really increased the potential for chaos. And in fact, the chaos is eventually going to arise in the system. Let's just watch as that chaos arises. So we might think, like with our 2 moons here, we've now been moving for about 4,000 ticks. Are they ever going to interact in a chaotic way, or are they just going to maintain this sort of stable interaction? And again, you know, if you're testing this yourself, you might say, well, this is long enough. Although maybe you can just see now that, oh yes, now it's become clear that they've all sort of been knocked out into slightly different orbits now. It turns out, actually, it looks like they've paired up a little bit. We've got sort of the 2 moons on the vertical axis in like a wider orbit. They're sort of speeding up. And then the 2, oh, well, they've switched now. The ones that were speeding up are now slowing down, and the ones that were slowing down are now speeding up. And this is the kind of chaos that we might expect. And indeed, even though we've paired off into 2 here, there's the potential that we could get even more chaotic interactions, and our 2 pairs split into, well, all 4 in different orbits. This is a good example of a case where we had what looked like spontaneous order or a stable orbit, but it wasn't. Truly, whoa, there we got almost a collision there for 2 of our moons, but the other 2 didn't collide. So we got sort of an interesting, or maybe they did and I just didn't see it, because they do seem to be still following the same motion patterns. And I guess we could watch this go for a number of ticks to see if this is going to be more chaotic or not, but at least we've already seen some of the chaos, that they're no longer in those same patterns they were in before, and they are now trapped. It looks like we got another slight interaction there that might be knocking. Whoa! We got 3. Okay, that's the chaotic interaction I was expecting, that I thought might come along, and now we basically have 3 distinct, or 4 distinct orbits. It might be 3, because I think that one might be gone for good. All right, I do want to finish with one final setup, which is I'm going to turn my initial speed to full, and I'm going to put us back on 290 degrees. Now maybe I should zoom out just a little bit here, because these guys are on pretty speedy now. You can see they're so speedy, they're outpacing their own initial positions, but they will arrive back in the same pattern that we saw before. One of our moons, the one that's in the front, is slowing down due to the gravitational force of the one behind it, and the one behind it is speeding up due to the gravitational force of the one ahead of it. Now, the interesting thing that we'll see about these 2 is that right about now, you can see by their lines, they're crossing over their old path. They've changed from speeding up to slowing down. If they were the speeding up one before, now they're slowing down. If they're the slowing down one before, they're now speeding up. And that's because they've sort of changed. They oscillate in their positions between whether they are chasing or whether they are being chased by the other moon. So we can now see the one at the top is sort of still in the chasing position, but it's going to get to a point here. It's due to the interplay of both their speeds. So the one that's chasing is the one that's speeding up, but then that means that its orbit is getting bigger. And if its orbit is getting bigger, it takes longer for it to complete its orbit. Likewise, for the one slowing down, its orbit is getting smaller, so it can complete its orbit quicker. And that interplay between those 2 changes the phase between whether one is following or one is being followed. And this switching back and forth, now the other thing that this is going to do is it's going to also change the angle between their orbits. And I've actually let this run for a very long time, so let's go and see. So I've got this now run here. It looks like 100 or 1.3 million ticks almost. This is after 1.3 million ticks. We can still see they're in a stable pattern. It's not a stable pattern where they're following the exact same orbit every time, like we did with our 2 started at 180 degrees. But it is stable in that they've never had a chaotic interaction. And in fact, their interactions are stabilizing themselves. What they're stabilizing, they're still going through that pattern of one is speeding up and one is slowing down. But what is happening is their two orbits are aligning with one another. The amount that one of them speeds up is no longer as fast as it was speeding up before. The amount that the other one is slowing down is no longer as slowing down as it was before. And eventually, I anticipate, although I can't, this is the point of the complex systems, is I have no analytical proof of this, but my anticipation is they might settle down into a perfectly stable orbit. And if they do, this is exactly the example of spontaneous order or self-organization that comes with, on the other side of the coin, of the chaos that comes from complex systems. And so sometimes I like to think of this as sort of two different forces, two sort of primary forces in the universe, two forces that we haven't actually spent a lot of time studying yet. The one force is the force of chaos, the idea that things are going to break down, stable systems are going to break down and be acted upon by their environment. This force of chaos we sometimes call the force of entropy, or entropy in thermodynamics or in other fields. The opposite force then is the force that creates order out of chaos, the force of self-organization. And that force, at least in terms of a scientific name, is the force of evolution. Evolution is, at least biological evolution, is the force that creates order, biological order, out of chaos, sort of the primordial goop that we started in, to create living organisms, and perpetuates order and pushes order into the future in a chaotic environment. So I like to think of these two forces as being two primary forces pulling in opposite directions. Entropy is trying to make everything get chaotic, but the forces of self-organization and evolution are trying to draw stable patterns together. And so to bring this all together, the stable patterns that we observe our solar system in, at least it observes to be stable, is really more likely to be close to this stable pattern that we're observing right now in my two moons orbiting this planet. It's stable, at least for the period of time that we've been able to observe it, but we're not ruling out the possibility that there could be some chaotic interactions between planets even that are orbiting. Now, my anticipation is that our solar system has already had all of its chaotic interactions earlier on in its life, when the formation of the planets and so on. And at this point, our planets, while they still might be oscillating like these two moons and maybe still trying to settle down into a perfect stable orbit, they have reached a orbiting pattern where there's not likely to be more chaotic interactions without there being some outside interference. And so this is what we might call self-organization of the solar system. All right, I hope you enjoyed this exploration of some of the key concepts in complex systems theory and our exploration of these simple orbits, so we could explore some chaos and nonlinearity. So thanks a lot for watching, and we'll see you in the next video.